How do you measure K? So that's the first concept here. Now, the measurement of K begin with understanding how K is related to flow rate in the systems. So that is based on Darcy's law. You know all Darcy's law from CE153, but I'll write it. So Q is the flow rate in a system through a porous media. Depends on three factors. First is hydraulic conductivity of a system. That is how fast water can move through that system. Then the hydraulic gradient. So that's the head is the dH is the change in head divided by L, and then area. So what it says that if you have a porous media, let's say this is the porous media, and how much water moves through the system depends on K as well as the area of the cross-sectional area, because the more the area, more water will pass through systems, and also the head difference between these 2 points. So if water has high pressure from left side, it will move from high pressure to low pressure, and that this is the length of the media. So that's here we write for a biofilters. We talk about DH is the hair difference between top to bottoms, and this G is the delta G is the change in distance or distance between 2 points. So if you rearrange the Darcy's law, you will get these equations. And now this equation you can use to determine K. So this is all about how to quantify K. But how about conceptually, how K is related to actual soil properties? We learned that K is related to porosity as well as particle size. But you should also know that K depends on properties of waters. So if you think of here, this is the equations. It states that K is hydraulic conductivity depends on intrinsic permeability. So this is intrinsic permeability of the porous media. So this is soil properties, which we discussed before. That's related to particle size as well as porosity. But if you think of this factor, one is density and viscosity. Those are related to water. Because you see, if you have increase in density of water, that will increase hydraulic conductivity because it has more weight to move, so it's easier to move. Same thing for viscosity. If you have high viscosity, it will have a lot of friction. So that means increase in viscosity will decrease hydraulic conductivity of the system. So viscosity can increase, viscosity can decrease if you increase temperatures. So that's why you can think that temperature can influence hydraulic conductivity best way. So because viscosity is inversely proportional to temperatures. So that means increase in temperatures would decrease viscosity. That means that will increase hydraulic conductivity. There are two different ways to measure hydraulic conductivity. As I said, you can measure flow rate, but it's how you change the hydraulic head is what determines the different types of laboratory methods. The first one is constant head. If you see, this is the biofilters. Let's say this is the soil media. That length is L. What you do is you pack them inside it, and then you add stormwater here. You wanted to ensure that these stormwater, when it's added, this will increase the head. But you wanted to maintain a constant head, which is here. That's the constant head with respect to your effluent, wherever that water exits the systems. That constant head is written here. And this is the area. This is the area. And this is the length we talk about. And then we're determining K here. The way you maintain the constant head is by increasing the flow rate here higher than it can exit here. So that means it will continue after it rise to this location, rest of the stormwater will drain out of here. So that means you maintain that constant head. So what you do is what you collect stormwater at certain time, so that you know the volume of stormwater you collect in specific time. That T and V will be determined in your experiment. You substitute value T and V, you know L, you know area, all that stuff. So all these things are constant. So that means you can calculate K. So that's one way. And you should know that you can use constant head when you have coarse grained sand. That means you have you have high hydraulic conductivity. You don't have to wait too long to measure certain volume. But this is not efficient when you have low hydraulic conductivity. That means you have to wait for a long time to collect certain amount of volume. And that would means you can't use these systems. So for those fine grain systems, you use sorry, K is low. That's a typo there. So when you have fine grain system, then you can use falling head test. Falling head test, the difference is you collect water here, you record time, but you do not want to measure the volume, because volume can be influenced by evaporations. So that's why all you have to do is record how long it takes from when the head drops from 1 to second one. Okay, and so those are written here. So this is H1, H2. Again, you can see these equations can be derived from here. If I do the derivations very quickly, dH over H would be cancelled, will be K over L time dt. If you take H initial, H final, T equal to 0 to T, this would be Ln H2. This will be H initial to H finals. So this will be H2, H1. Okay, so that will determine K would be L over T ln H2. Okay, so this H1 is initial H. So that's the final H. So this should be actual. There is a typo here. It should be H final. Initial. Okay. All right. So you can determine that. You know the L, which is the depth of your filter media, time you record it, and these are the head you record in the experimentally. So these are two methods. In field method is very similar to the lab methods, in the sense that you can't really collect water at the bottoms, but you can measure the time it takes to infiltrate into ground. So here is the same concept. Either you has a borehole, which is here, and you add certain amount of water at a constant head, and then you see how long it takes for that head to for the water to go through that systems. And same thing you can also do for a double ring infiltrometers. The idea here is that you add water in one rings and see how long it takes for that for water to come to the same head in the other side, and that will determine your hydraulic conductivity. Again, these are different tests. You can search online how to measure hydraulic conductivity in a system in a field conditions. You will be able to understand it. The concepts are same. Here is an example where we determine hydraulic conductivity in our lab using a falling head test. Here it gives you all the parameters. It says L equal to 42 centimeters. You have also, we have given you The diameters of biofilter is 5 centimeters. So that's 5 centimeters. That means you can calculate area. So that's pi d squared by 4. You also know H1 and H2. Um, so you use the equations to solve for that hydraulic conductivity. Again, L is given, which is 42 centimeter. T you calculate here. That's what you measure experimentally. You know H1, H2. You plug the numbers, you get the answers. So you'll get answer for different K here, and then you can take the average for all pi. That's very easy. The second question is how long it would take to drain 20 centimeter of ponded water above a bioswale if the hydraulic conductivity of soil is 1 centimeter per hour. So you have a bioswale, let's say this is bioswale, and you have water height, which is here, that's 20 centimeter. And assume complete saturation of soils. So that means you can say you need hydraulic gradients. And the pipe that divert the water is about 50 centimeter or 0.5 meter below the surface. So that's the L, that's the depth of the filter media. And so let's see. So you were asked how long it would take to drain the system. So that means you want to see how long the head will drop from here to all the way here. So that means that initial head, if you write here, initial head was H1, final head is H2. So H1 would be 50 centimeter plus 20 centimeter of column above it. So that would be 70 centimeter. And its final would be 50 centimeter. You know L, which is 50 centimeter. We asked you to calculate time. So again, this is a falling head method. If you see the falling head method was the equations, that would be K equal to L over T times ln H2 minus by H1. So if you write that here, K equal to L over T ln H2 by H1, time would be L over K ln H2 by H1. L is 50 centimeters, K is 1 centimeter per hour, ln H2 was the final height. Final height is H2, so which is 50 divided by 70. You should get that answer here in terms of hour. So that conclude our the segments on hydraulic conductivity.